Good morning, everyone. Welcome to our webinar today on concept commercialization. I want to thank everyone for joining us today. My name is Mauricio Villegas, Business Development Manager for Koch Modular. And again, just want to thank everyone for joining us today. This is the second webinar of a three-part webinar series we've been holding. We started doing these webinars going into COVID and been doing it now for almost 3 years now. And I want to thank everyone's participation. It's always been well received, and these are the three that we try to repeat every year. Last month it was liquid-to-liquid extraction technology. Today is concept commercialization, and in December we'll be doing one on distillation techniques. So again, thank you, everyone. Talk a little bit about logistics. We have a chat window open. If you have any questions, feel free to type them into the chat window, and we will leave a few minutes at the end of the presentation to review your questions to Chris. And if we don't have time to address all the questions, we'll respond to all the questions after the webinar by email. So again, thank you. So please hold your questions to the end. Before I introduce Chris, just a little bit of a summary on who Koch Modular is. Basically, we're a joint venture company with Koch Modular. That's where the Koch comes from. We've been in business now for a little over 40 years. About 20 of those was when we became that joint venture with Koch Modular, and now Koch Modular Process Systems. I'll go briefly into our capabilities and expertise because Chris will be talking a lot about this during his presentation. Process engineering, our company is predominantly managed and run by process engineers who have expertise in distillation, liquid extraction, gas absorption, and thermal design. We also support that with pilot testing, which is very important when you're trying to commercialize systems. So we have a pilot plant located here in Houston. And then all our projects are delivered modularly. So we don't stick build anything, everything goes out as a truckable module. So I guess that'll kind of sums up into our core strength, which is process design, pilot testing, which then is backed by a process guarantee. And then you get project certainty and cost savings through modular delivery. So that's enough about us. Just to introduce Chris. Chris has been with us for a few years now. Chris graduated from the University of Michigan, holds a chemical engineering degree. For about 15 years, he's been working for various companies, including Dow Chemical, Origin, and BP. He brings a lot of experience in taking projects from concept to commercialization. So very a good person to be talking to us today about that specific topic. So with that, I'll hand it over to Chris. Thank you, Chris.
Great, thank you, Mauricio. So today's talk on process development and scale-up challenges will roughly break into two parts. An early part on solvent selection and modifying a chemical reaction or separation to ease the process scale-up design. And then the latter half will talk about equipment selection and metallurgy. So just so that we're all on the same footing with one another, what do we mean by process development? You may be familiar with the technology readiness level or the TRL scale. This is used by NASA or perhaps the Commercial Readiness Index, CRI. In general, I would say technology or process development is occurring once a chemical process has reached TRL 4 and it is trying to go to 5, 6, 7, 8. This means that a chemist or a team of chemists has successfully demonstrated the reaction at bench scale using beakers, 100 milliliter round bottom flasks, that sort of scale, and now it's time to move it into 100 liter or 1,000 liter reactors with the goal of eventually scaling to commercial scale. When things are smaller or earlier than TRL 4, this is still the technology catalyst development ideation stage. Different concepts are still being tried, and when you're later than TRL 8, you already have a manufacturing plant, and at that point you're replicating, doing minor improvements in efficiency or yields to become more competitive. So doing process development from TRL 4 to 6 is an exciting time because you have a lot of leverage. A lot of small decisions can have large impacts on how much the process will cost either to build or to run. We're going to go through a few examples of that. Process development qualitatively could be thought of as conceptualizing a process, putting together the very first version of a flow diagram, doing the very first version of a simulation to show where the heat and energy and the difficulty of the separations emerges usually in that first process simulation. Process development also includes the very first time you're going to select your particular unit operations. And we'll go through a couple of examples later in the talk of how do you even choose the right filter or the right heat exchanger for a particular process you need. And often piloting is going on for the first time during process development. And piloting has all the same challenges of a commercial plant design. You have to select all the equipment and get it to work and put it together. So let's take an example. This is an expired patent I pulled off the internet. It's an oxidation reaction of cyclohexane to adipic acid. Suppose you were the chemical engineer who was presented with this chemical reaction and you were interfacing with the team of chemists who had just finished developing this to the 100 milliliter wet bench scale. What might be one of the first things you do or ask for? There's likely to be a separations downstream to recover and purify the adipic acid, and knowing what you're separating from is important. So it would be nice if the chemist team provided you with a list of not only the desired products, but the concentrations of the impurities that are in the reactor effluent stream. That table is nice, but I recommend asking to see the chromatogram. Oftentimes it will be an LC liquid chromatography or GC gas chromatography chromatogram that analyze the reactor effluent, and it will show the peak of interest, but also you don't have to know a whole lot about chromatography, but you can get a great deal of understanding of what's in there by pointing out certain peaks. What is this? What is this? Things that elute late out near 14 and 18 minutes. The x-axis here is minutes. Those are higher boiling or heavier compounds. Things that elute early are lighter boiling compounds. And you want to just reconcile what the chemist is telling you with what you see in the gas chromatogram or liquid chromatogram. The next thing I would recommend is always ask the question, what about heavies and inorganics? If a compound is too large, too high molecular weight, or too high a boiling point, it won't be resolved on the gas chromatogram. It'll just get stuck in the trap on the column. And it's unfortunately been my experience that those compounds aren't necessarily appreciated until much later in the process, perhaps when piloting has occurred and someone's wondering why there's a thick sludgy material at the end of the distillation. This might have been discoverable earlier on if someone had asked, does this chromatogram resolve all the heavies that you're making? And inorganics, similarly, like salts, do not resolve on a gas chromatogram. So you want to ask about those as well, because they will be part of your separations challenge, even if they don't show up on the analytical analysis. The next thing I would do would be to scrutinize solvent choices. Since this is an oxidation, my expectation is it is analogous to terephthalic acid oxidation to make polyester. That reaction, or terephthalic acid, which is a monomer for polyester, that reaction is well known. There's hundreds of operating facilities today that conduct this reaction, and it is done in acetic acid solvent. So it would be my expectation that this patent, which is doing a similar oxidation, probably uses acetic acid. And indeed, when I read the abstract in the final sentence, you can see this was done in the presence of acetic acid. Now, alone, that might not pose a problem, but in the third to last sentence that I've highlighted, you can see the patent suggests they will be separating and recycling unoxidized cyclohexane. So if we want to recycle cyclohexane in the presence of acetic acid, is that going to be problematic? And this is one of the next questions I would ask as a process development engineer. In fact, the vapor-liquid equilibrium plots show that we have an azeotrope. On the left, you can see in the TXY plot, we have a maximum boiling azeotrope. And on the right, XY plot, you can see the curve passes through the y = x 45-degree line. So this is indicative that there's an azeotrope. And this means if you were trying to recycle unreacted product, cyclohexane, if the concentration of that unreacted cyclohexane were, say, 10 weight%, your distillation tower would produce a pure acetic acid distillate, but a mixture of acetic acid and cyclohexane as the bottoms product. roughly 40% by weight cyclohexane, 60% acetic acid. And that's not usually desirable. Usually you want to completely segregate the solvent and the unreacted raw material so that you can add them back to the reactor at some prescribed ratio, not the ratio governed by an azeotrope. So process engineering might ask the question, is there a substitute solvent for acetic acid that would work just as well from a chemistry standpoint, but doesn't pose this difficulty during the recycle? We could still design a process to separate this azeotrope. It might involve bringing a third compound in and doing some sort of extractive distillation or using an entrainer or something like that. But what if we could make our life simple and just avoid that altogether? A reasonable suggestion might be to increase the carbon count of the acid species by 1. Instead of using acetic acid, let's look at propionic acid. So the lower charts here on the left lower panel is the TXY diagram for cyclohexane propionic acid. And we can see it lacks the high maximum boiling azeotrope now. We have a not quite, but nearly ideal open envelope here. And on the right, the XY diagram shows that these are now separable. The bottom's product will be pure acetic acid, and the distillate has a little bit of a pinch up here. This, you can imagine, it's not drawn in, but you can imagine stair-stepping the McCabe-Thiele diagram. And as you march towards the upper right-hand corner, the VLE does pinch. So maybe a 95% cyclohexane, 5% propionic acid distillate can be produced from this particular set of VLE data. And that may be acceptable. But you've achieved nearly a complete separation now between your unreacted raw material and your solvent just by making a very subtle solvent switch. And if you're still at TRL4, meaning we haven't yet graduated from the lab, we haven't yet done very expensive process engineering design, the pilot hasn't been built, this is a simple thing to go back and check. Once you're further down the chain and the pilot's been built and the engineering is done and the site has been chosen and the capital project is authorized, these kind of switches become virtually impossible and at least very expensive and causing of delays. So the earlier they can be contemplated, the better. All right, let's zoom in on this pinch a little bit here. Supposing they like the idea, but 95.5 recycle is just not going to work. That's okay. Chemical engineers have a big bag of tricks. So what can we do to relieve the pinch at the cyclohexane-rich end of the spectrum? This is a different system now, but it's analogous nonetheless. Reducing the pressure in a distillation tower usually opens up the VLE envelope, and you can see what was an azeotrope became a pinch as we lowered the pressure here from the pinkish line to the medium colored line. And as we lowered the pressure even further, even the pinch opens up. So going under vacuum conditions can be a useful solution to increasing the relative volatility. That probably means you're going to be switching from a trayed distillation column to a packed distillation column. So you can see packed elements on the left here. And that's okay. That's a necessity of the fact that you want a lower pressure drop when you have a vacuum distillation. Trays have about 10 times as much pressure drop per theoretical stage as packed columns do. So this could be a solution to relieving the pinch. It's a general rule of thumb that reducing the pressure of a separation increases the relative volatility between the two species. You often end up needing fewer theoretical stages and/or less reflux. This can be most easily demonstrated if you're looking at a Koch chart. The y-axis here is incremented per the log of vapor pressure. So we have log P on the y-axis, and the x-axis is spaced out as 1 over T in absolute temperature terms, although it's displayed in degrees Fahrenheit. When you have log P versus 1 over T, this is effectively turning the curved line you would see on an Antoine equation plot into a straight line. It linearizes VLE data, and you can see you get nearly straight lines for a given compound. And choosing a point at the high pressure, high temperature end has a smaller gap between any two given compounds than the low pressure, low temperature end. So provided the VLE lines are not parallel, they do in fact diverge at the low pressure end, you can usually enhance the separation by reducing pressure. There's a bunch of known compounds on this plot, and that makes it easy to design for them, but occasionally a process engineer will be faced with the task of designing for compounds that are unknown. And it may be necessary to go into the laboratory and generate your own binary pairs so that NRTL, the non-random to liquid model, can predict the VLE behavior. This is not an easy task. You must carefully set up and operate an apparatus so that you don't have any theoretical stages. You want to put the vapor and liquid in perfect equilibrium. And unfortunately, it's a common mistake or common unknown or oversight to have half of a theoretical stage in your VLE apparatus, and that will give you the wrong results. So the founders of Koch Modular published a paper almost 30 years ago. It was 1995. It's still available in Chemical Engineering Online, that teaches how to very accurately and successfully measure binary pairs through a VLE still apparatus operation, and gives the example on the right here. Not everyone has the apparatus or the desire to measure their own binary pairs. So when someone comes to Koch Modular, we offer our services in our pilot line of measuring these binary pairs on the client's behalf. We've done them many, many dozens of times successfully. And the neat thing about accurate measurement of binary interaction pairs is they essentially enable a scale-up factor of infinity. If you know the behavior of vapor and liquid at this small scale, you can design any size distillation tower you want. You don't need to pilot it. That's rather unique to distillation. The process engineer may suggest substituting a solvent for other reasons besides azeotrope. For example, chemical compounds have widely varying odor threshold ranges. Threshold limit values are the maximum, the TLV in the second column here. Tells you the maximum ppm to which a worker can be exposed. We also have the IDLH, the immediately dangerous to life and health. And then on the table 3 on the right, we have the maximum allowable effluent concentrations to waterways before they are toxic to aquatic life. So if your process has a wastewater discharge stream, it may be useful early in process design to find out what are the discharge limits for that compound, and do you have a process operation that can readily achieve those limits. It may be wise to substitute solvents for something that has a 10 or 100 time higher discharge limit, particularly if the separation for removing that from the wastewater stream is a difficult one. All these tables and more came from the Ian Smallwood's Solvent Recovery Handbook. I've referred to this book any number of times when I'm trying to substitute a solvent or get away from an azeotrope. It's a handy reference. Another task we might want to do is get rid of a solvent entirely. It's quite common for a process at TRL4 at the bench scale chemistry. The chemist has selected a solvent to produce a product, and those two, the product and the solvent, will be similar compounds but not identical, meaning they're trying to, for example, they're trying to produce propionic acid, and they did the reaction in acetic acid. Those two can be resolved by analytical techniques, and it's very easy to tell how much propionic acid did I make because it's not overlapping peak with acetic acid. But we don't necessarily need that capability in a production scale. If you can run the reaction in the product, then why not do so and save yourself an extra separation? This is not a good idea if your reaction is equilibrium limited. Reversible reactions, if you flood the reactor with product, will tend to drive it in the wrong direction, and the product forms instead of the reactants form instead of the product. So we don't want this, we don't want to suggest this for a reversible reaction, but for irreversible reactions, this can be a very clever trick for eliminating a separation. Sometimes a two-step reaction will involve a solvent swap. So for example, if reaction 1 is A plus B goes to C, and that's conducted in water, and then C is further reacted to form compound E, and that's done in a different solvent for some reason, diacetone alcohol, for example. Diacetone alcohol has a higher boiling point than water, 166 Celsius compared to 100 Celsius. This makes a solvent swap trivial and straightforward. You would take your mixture of C plus water, mix it with diacetone alcohol, and feed it to the distillation tower. Take the lightest boiling species, which is water in this case, off the top. We're assuming C is a heavy boiler here, and that one's carried out at convenient concentrations for the next reaction in diacetone alcohol as a bottoms product. But what if the reverse were the case? What if reaction 1 had been developed in diacetone alcohol and reaction 2 had been developed in water? It is not possible in this case to feed the water into the mixture, into the mixed C plus DAA stream, because water will just come off as the distillate, leaving C in the same solvent it started in. Process engineers will recognize this challenge. It's not always appreciated as a challenge if you're in the chemistry lab doing bench scale chemistry, because this is commonly encountered where a chemist finishes their reaction in diacetone alcohol, puts it on the rotovap, removes all the solvent. They're left with a crystal or an oily solid or some other coating on the glassware that's the product C, and they just reflood the flask with the next solvent, swirl it to dissolve, and move on. It's a very simple and straightforward process, but it represents a significant scale-up challenge. Taking a stream and concentrating it to an oily solid or a viscous liquid only to redilute it in the next stage. We'd like to avoid this if we can. So how would we get around it here? We might suggest a different alcohol that's lower boiling than water. For example, methanol, which does not form an azeotrope with water, and again, restores the trivial separation where we just mix in the water with the C and methanol stream, distill off the light boiling methanol, and carry C onto the next reaction. Chemists may object, say that methanol is too polar, or for some other reason. There are other alcohols we might consider. We might go to the next less polar alcohol, ethanol, but we should be aware now we've just encountered an azeotrope with water. Water ethanol azeotrope is about 95.5. I don't want to represent that we'll distill to 95.5 because it takes an awful lot of stages to get to the azeotrope, but getting to 93.7 is pretty straightforward. So if I were asking the chemist to retest reaction number 1, I would not want them testing dry 200 proof ethanol. I would request that they do it in 93.7 wet ethanol, because this is what I can readily distill from that mixed system. We can go one alcohol higher, IPA. This one forms an 85.15 azeotrope with water. The water is making things more polar, so it's probably getting less attractive, but nevertheless, if one of these 3 works, it's a quick win that's going to greatly simplify your process design. So that makes them worth trying early on. So at this stage, I'd like to transition to equipment selection and talk a little bit about how one faces the challenge. We've left the process technology stage, the solvents are chosen, the chemistry is locked down, and you've got these blocks on the block flow diagram that say filter underneath them. How do you choose what piece of equipment is going to suffice in that block? What are you going to build from a pilot scale perspective? Filtration means solids, and solids are usually the bane of chemical engineers' existence. Projects tend to have higher failure rates when solids are involved, but at some point, you're probably going to encounter them. And there are a myriad of filters to choose from. You can find on the market pressure filters, rotary drum vacuum filters, Roseman-style Rentsch filter in the upper right. Middle left is a pressure relief filter, middle is a candle filter, middle right is a Schenck filter, bottom left is indexing vacuum belt, chamber press, and then inverting basket centrifuge. The challenge here is probably any salesperson you would care to call up tells you that their filter will work just fine for your application. And chances are they're right. Some scale probably works. But these filters represent 2 to 3 orders of magnitude of cost difference. That is, if you were to take the purchase price for the most expensive filter on this slide and divide it over its active filter area, so dollars per square foot of filtration area purchased, it is 1,000 times more expensive than the least expensive filter on this slide. So it behooves the chemical process engineer to make a wise selection of what type of filter we're going to scale up with here. A good starting point is to take a look at the particle size distribution, the PSD. Are we just trying to get the big stuff out on the right, or do we need to get that thin tail of fines on the left out as well? It's an important question to ask, and it depends on the product specification and the sensitivity of downstream unit operations to these fines getting through. If you're in a large organization that has filter experts that design these all day long, then your life just got really easy, but not everyone is afforded such a luxury. So you may have to proceed to forming an opinion on what type of filter to use on your own. And in that case, the laboratory can usually provide a Buchner funnel style constant pressure filtration apparatus. There's a vacuum applied to an Erlenmeyer flask, which is beneath a sandwich filter element or filter paper. And then the slurry is fed to the top unit there where the blue lid is. And someone with a stopwatch and a graduated cylinder, a graduated flask can take notes on how many milliliters of filtrate have passed through per unit time. And with that information, you can, this chart comes from a paper in the AICHE journal from 1956, so it's some 70 years old, written by Grace. With that information I've just described from the system on the right, you can plot the data two different ways. The two upward rising curves here are the same data, just plotted against different axes. You take the incremental time per unit volume filtrate, time per volume, and plot it versus total cumulative filtration time, or plot it versus total cumulative filtration volume, T over V versus T, or T over V versus V. That is, it tends to be the case that one of the two of those will be a straight line. In this case, T over V versus V, the blue curve, is the straight line. And that tells you something about the mode of filtration that's going on here. In the T over V versus T case, the red line case, if that one were the straight line, it would be indicative that as the cake builds up, the porosity of the cake is changing. It is shrinking with time. Very common to see this in polymers and other soft solids, viscose rayon, celluloses. The cake is compressing, or the pores between the particles are collapsing, and the resistance of the cake is changing with time. If you contrast that with the blue curve, the resistance of the cake is not changing with time, it's only changing with cake thickness. The cake is sturdier, the pores are not collapsing, and so the only issue you have to contend with is a cake that's twice as thick has twice as much resistance as a cake that's half as thick. So this can guide you in the selection of a filter. Some of these filters are amenable to having very thin cakes and are better choices for standard blocking, the T over V versus T, the red curve. You're probably going to be designing for a thin cake filter. The blue curve, T over V versus V linearization, does enable you to generally choose a thicker cake filter. The red curve is going to be more amenable to filter aid. That's the cases where I would recommend trying filter aid to get some structure in that cake to prevent the pores from collapsing. The blue curve, probably less of a benefit for filter aid. So this is just a simple example of using underlying physics, the properties of the slurry, to help guide the choice of a filter in a way that's perhaps contrary to our intuition. What I have tended to observe is engineers like to go back and use what was familiar. So if you have an engineer that used a candle filter on a previous job, they're 100 times more likely to recommend a candle filter on this job because they've seen it work before and they're comfortable with it. But that's not the best way to do unit operation selection. The best way is to measure something important, something physics-based about your system, and then match it to a piece of equipment based on those properties. And to do that, well, let me give another example, and then I'll talk in general on how to do that. You would face the same challenge if you were designing a reboiler for a distillation tower. So reboilers, condensers, there's multiple different configurations, horizontal and vertical, but then there's also different types if you're in the reboiler. So reboiler might be a thermosiphon, might be forced circulation, falling film, or kettle style. In a thermosiphon case, the liquid circulates automatically because the boiling fluid is less dense, and that creates a pressure gradient, and so everything starts to move on its own. Forced circulation involves a pump, so does falling film. A kettle does not involve a pump. It again is just using gravity to separate the vapor in the liquid and spilling over a bottoms product. So how do you form an opinion? Which one is the right one? There are too many factors to consider here, but let me give one story that illustrates why this is an important question to consider and not just fall back on what was familiar and what was used last time. There's an excellent illustration from a Henry Kister article in 2017 where a parallel thermosiphon reboiler train was found to stall out every time the plant turned down to 50% capacity. They would try to turn it back up, and one of the two trains would be dead. It would not be boiling anything, so all the load was on the opposite side, and that load was, or that one side by itself was insufficient to achieve nameplate capacity on the distillation. It forced them to shut down, drain the shells on the stalled side, refill them, and turn it back on. What's going on here? Well, there was a very wide boiling point difference between the compound that was boiling, ethane, and the compound that wasn't boiling, the heavier hydrocarbons. So when you have a wide boiling point difference, it makes you ask the question, can the steam utility or the hot oil utility that's providing the heat to the tower boil both components or only one of them? In this case, it could only boil the lighter component, and at turn down conditions, there was insufficient circulation through the loop to keep enough of the light component re-entering the reboilers, so it would fill up with the heavier component and then boiling would stop. And if boiling stops, circulation stops because this is a thermosiphon. So in general, it's not very wise to match thermosiphon reboilers to a service where you have a wide boiling point difference and you can't boil one of your two components. You want to be able to boil 100% of what's in the system if you're using a thermosiphon. Not all of these types of equipment are necessarily in all of our heads. So how do you gain an understanding of what's out there? What are your choices? I recommend finding or building an equipment taxonomy. Taxonomy starts from a high-level type, for example, column contactors or liquid-liquid extractor, and then breaks it down one level or one type at a time into substages, static and agitated. And then among static extraction columns, there are three different types: spray, packed, and tray columns. Among agitated, there are also three different types: pulsed, rotary, and reciprocating. These 6 types at the bottom of the taxonomy all have their specific advantages and disadvantages, and hence find their way into specific applications in refining, petrochemical, nuclear, and chemical industry. If you're lucky, you can find a taxonomy with a nice couple of pages of write-up on how the advantage of one particular type means it's most commonly used in pulp and paper or most commonly used in some sort of petrochemical use. This lets you look at those criteria and then compare it to the process that you're doing scale up and design for and say, okay, based on the advantages here, I'm going to match it to this particular application, as opposed to saying, what did I use last time? I used a rotary last time, I want to use a rotary this time as well. We want to, as much as we can as engineers, we want to break away from always repeatedly using what's familiar, because we'll probably eventually encounter a case where it's not helpful to do that, and instead always rely on matching the best possible unit operation to our particular challenge. Since Koch Modular sells a lot of extraction equipment, being the sole worldwide licensor of Scheibel columns and car columns, we have strong opinions on which type of column will be best suited to, for example, a high viscosity situation or a low interfacial surface tension situation, or a situation where we're height constrained and we really need a large number of stages packed into a very short column. We can make recommendations along these lines. Okay, I'm going to switch now into talking about corrosion data, because we can't choose a filter and we can't choose a heat exchanger or an extraction column if we don't know what materials of construction are suited to your particular application. And unfortunately, corrosion studies tend to be a bit of an afterthought. A lot of engineering gets done, a lot of process design gets done, and now someone wants a cost, budgetary estimate or a firm price on what this system will cost. Almost impossible to render such a cost unless you know what materials you're building out of. So I recommend early on, again, all the way back at TRL4, we've just left the laboratory now, what are the corrosion rates that these solvents or raw materials or products represent to the common metals that we build out of? On the left here, I've grabbed a few photos from an Oak Ridge National Laboratory report with hydrofluoric acid, and you can see it's pretty aggressive on the metals. So back in the 1960s, they were trying different metals, trying to figure out what resisted hydrofluoric acid. Those coupons show dramatic metal loss, and probably qualitatively on their own can be discounted as used for construction and scale up. However, some of the more modern alloys may show little, if any, tarnishing or damage, and so we determine whether or not they are suitable based on weight difference, weighing the coupon before it goes in, weighing the coupon after it comes out of a 200-hour corrosion exposure. You have to be careful when you do this, however, because there may be deposits on the metal, a film or an oxide or an adherent layer, and it could be the case that the amount of metal loss is roughly equal and opposite to the amount of mass gain from deposits, and that will give the impression that you don't have a corrosion problem. people skilled in doing corrosion test and metallurgy selection know to look for this and know that the deposits should be removed. If you want a procedure for how to do corrosion testing, complete with all the gotchas and rookie mistakes spelled out, the Materials Technology Institute has a nice PDF on their website, the Field Corrosion Testing of Metal Alloys PDF. And I recommend consulting with this document to make sure that corrosion tests are carried out in a way that produces usable data. I've referred back to this diagram any number of times when a client is not sure even what metals to test. What do you recommend, they say. Koch Modular doesn't specify metallurgy. We don't have any staff metallurgists or materials engineers, but nevertheless, we can provide a little bit of guidance, and other engineers doing process design and scale up should be at least familiar with the types of metals that are out there. So carbon steel is probably the most common metal used in petrochemical process systems, but if it is corroded by the contents of the reactor, we can go to successively higher and more expensive alloys. Now, as we go upwards on this diagram, if we go upwards and up the right side, this is the side that's going to be higher in nickel, ultimately culminating near titanium at the top. And this is very appropriate if you have halide acids, hydrochloric acid, hydrofluoric acid, hydroiodic acid. These acids, once they give their proton to the metal and do their corrosion, they're done. Chloride doesn't do further chemistry on metals. And so they're sometimes erroneously referred to as reducing acids. All acids are reducing. These ones are just non-oxidizing on the right side. On the left side, by contrast, we have nitric acid, chromic acid. These acids are oxidizing acid because, for example, nitric acid, after it gives a proton to the metal as a corrosion agent, the residual NO3 anion can do further chemistry. It can give an oxygen up as well, which would then lead it to evolve NO2 gas. So because the anion also participates in corrosion, it is an oxidizing acid. In the case of oxidizing acids, you generally want higher and higher chromium levels to resist the corrosion rate. And if you have no clue whether you have an oxidizing or non-oxidizing acid corrosion mechanism going on, people choose from the middle of the Y, the metals that are resistant to both. At the bottom of the both resistant spectrum, we see 316 stainless steel, and at the top, everyone's pretty much heard of Hastel AC276, sort of the jack of all trades, king of corrosion resistant alloys. So those two metals get chosen a lot. There are very deep and plentiful supply chains for alloy C276 and 316 stainless steel. It's quite common that corrosion rates won't be fully understood or won't be studied across many alloys. It'll sort of just resort to 316 and C276. So I recommend always testing 316 and 276 in addition to whatever else you're going to test. Test as many metals as you like, but don't leave those two out, because there will come a day where you're trying to find a particular fitting or a particular instrument or a 90-degree elbow with raised face flanges and a 300-pound pressure rating, and it's just not available in some of the lesser known alloys, but almost guarantee you'll find it in 316 and C276. So test those always in addition to whatever else you're testing, so that you have some future options available when it comes time to build the system. Process engineers doing scale up should also be aware of cracking. It's not enough to just test for wall loss. If the corrodant forms cracks in your metal, that won't necessarily show up in a weight loss test. It tends to be the case that either welds or the heat affected zone around the weld are the most susceptible to cracking. So you can pick this up in a more rapid test by using a welded and stressed coupon. The diagram at the top shows the fillet weld, and then the welded section is then bent into a horseshoe shape to put it under stress. There's a lot of tensile stress on the outside radius, which once subjected to a corrodant should rapidly show cracking phenomenon if it's going to occur. Probably everyone's heard of chloride cracking for stainless steel. All austenitic steels are susceptible to chloride cracking, but there are about 10 or 12 known cracking mechanisms. So amines and ammonia are known to crack brass. Caustic and ethanol at high enough temperatures can crack carbon steel. Methanol can crack titanium. There are sort of a marvelous and wide range of cracking mechanisms, and you don't want to use a metal that's very robust in terms of mils per year. Wall loss is negligible, but it has a cracking susceptibility. This is a difficult thing to learn, and you want to consider the OD and the ID as well. When you're building out of stainless steels, it has been the case that people spreading de-icers, calcium chloride or sodium chloride de-icers, the melted snow drips through and gets under the insulation and cracks things from the outside. So consider the outside diameter and the inside diameter when choosing metallurgies here. We've gone through an awful lot. All of these fit into process development. Of course, if you're past TRL4, the engineering's been done, and it's time to build. We Koch Modular are an EPC. We do design and build and do all the systems integration, instrumentation, and DCS programming to get a chemical process system up and running. But I enjoy getting involved with clients back at the TRL4, TRL5 level where the conceptualization of the process is going on. So the earlier I can engage with a client, the more these questions can be asked, these solvent substitution questions, metallurgy questions, raising all these issues which have high leverage, high chances of reducing the capital cost or operating cost, which in turn increases the success likelihood of any given process getting built. Things that are too expensive is the number one reason things don't get built these days. So good process development, technology development early on gives you a higher success rate on your projects. We all like to work on things that are going to get built. Koch Modular does 3D design, complete 3D layout, so you can walk through modules in 3D before they're built. These modules are as small as indoor pilot scale demonstration units on the left, medium scale distillation extraction units like the 3-module plus stair tower one in the middle, or 20 plus module integrated systems producing multiple products. We've done all of the above. All modules made by Koch Modular are road truckable. We can build them in multiple different shops across the United States or Europe or Canada. The modules, once completed, are driven via truck on site. They're the right envelope size to fit under US bridges and can also be packaged and put on boats and shipped overseas. And then cranes will erect them and set them on a foundation. A pair of cranes can put up 3 to 5 modules in a day. Koch Modular supplies all the interconnecting spool pieces between the different modules, as well as the deck and flooring and railing between the modules. So 90% of the field construction is eliminated using modular approach. And that concludes my process development talk. We've left the chat open here for a few questions.
Great, thank you, Chris. Thanks for sharing your experience and your expertise with the group. Do have a couple questions for you. The first one would be, do you know of any examples where piloting really didn't help the situation?
I know of one story where a pilot line was built and it was operated, and more or less the products coming out of the pilot line were successful, and there was never a deconstruction or opening of the pilot equipment afterwards. So when the eventual commercial system was built, there were these filter baskets that endlessly filled up with, they were corrosion products. They were iron salts. The plant was corroding and plugging up the filter baskets. And the plant manager was standing there saying, didn't anyone find this at pilot scale? So they went back to the pilot line and took the heads off all the heat exchangers in the pilot, and sure enough, every heat exchanger was full of corrosion products that had just never been observed because no one looked at them. So it's an example of building a pilot and then not learning perhaps what should have been learned from a pilot operation, which is unfortunate. So take your pilot line apart and look for problems. Don't assume they're going to pop out.
Mm-hmm. Great, thank you. Another question is, are you aware of any pitfalls that we should watch out for when we're trying to take something through concept into commercialization, that it's like, oh, if we had done this, you know, things would have turned out so much better?
Yeah, there are many of those types of pitfalls. So, well, one would be flexibility. If you can build a system that can flexibly handle the top 3 best extraction solvents or the top 3 organic acids as solvents, as opposed to only being able to handle one, or something that's a little bit future-proof in that regard. It wasn't just a one-trick pony plant. I think that can be useful. Another thing that often gets overlooked and is a source of regret is there's a one-way trip through reactor 1 to the intermediate tank, and from the intermediate tank through reactor 2 to the product tank, with no consideration of what happens if the intermediate was off spec. Is there a way to get it back into reactor 1, or is there a way to get it back upstream to the feed tank? It's one extra pipeline and one extra valve that should be on the P&ID. And when that gets overlooked, you end up with someone stringing 100 feet of hose in the plant, and it's an opportunity for injuries and leaks, and causes some difficulty and heartache that could have been avoided had someone, anticipated that in the real world, 5% of batches are off spec, and you need to be able to do something with them.
Great, thank you. We have another one that just came in. Do you ever build a process module in shipping containers and deliver overseas?
Yes, modules are built for overseas delivery. They're not built in shipping container size, which is a little smaller than a process module, but we can make a module seaworthy in its packaging so that it can go on the right kind of ship and go overseas.
Thank you. One other question is, what factors can improve time to market? So a lot of times when you're going from concept to commercialization, time to market is very important, and the sooner the better. So what steps can be taken to make sure you get there as quickly as possible?
Get your corrosion test done early. Get all these process development questions answered and asked and answered early, because nobody likes to incur a 6-month delay while we go back and restudy a solvent change that represents a multi-million-dollar CapEx savings but hasn't been looked at yet. I mean, then modularization alone can accelerate the delivery of a process plant, because it is possible to do your on-site foundations, roadways, drainage construction in parallel with your process plant construction, because they're happening in 2 different places, and then you put them together at the end. So very common to see 25% schedule telescoping or contraction using a modular approach. And I see a module dimension question just came in. The maximum size module we build that'll still go over a roadway is 11 feet by 14 foot in its footprint by 80 foot long. That's as big as you want to do. It's easier to do a module that's in the 60 to 70 foot length and 11 by 13 foot, I would say.
And I'll add to that, if there is a particular column or vessel that is too large to go inside one of these road truckable modules, we can do also what we call a hybrid, where we'll have the column fabricated offsite, delivered along with the module, and then stood beside the module. So there are options for those instances where a column may just be too big. I think a typical column, the largest column we can put in a module is about 6.5 feet. So if it's considerably larger than that, it'll be freestanding alongside a module. Another one just came in. When choosing equipment in the conceptual stage, do you have a recommended source for equipment costs?
Yeah, equipment cost is always a thorny one. So, all right. On one hand, knowing your equipment costs gives you a bit of a false sense of knowing your whole system cost, because actual major pieces of equipment are only going to be 1/6 or 1/10 of the overall system cost. You have a lot of engineering hours, you have a lot of structural steel and piping, a lot of time consumed doing the programming. Instruments are expensive. So we focus on equipment so that we can apply a multiplier. And that multiplier, I've seen people use a multiplier on their equipment costs as low as 3 and as high as 10. And there are vigorous debates on what the right number is. So on one hand, equipment costs, especially approximate equipment costs, can be misleadingly helpful. On the other hand, I would say that the fastest way to build up a quick library of equipment costs for a process is to call up some vendors and ask them for budgetaries. You don't want to ask them for firms. That takes them a long time and it's a lot of work, and you lose a lot of goodwill if you don't end up buying it after they put all that work in. But if you can get indicative budgetary pricing or order of magnitude pricing, particularly over the phone, that's a good way to start. And if you can't get that, I recommend asking them for the weight. Can you at least tell me how much your machine weighs? It's a common thing that the price is directly proportional to its weight, and process equipment tends to cost between $8 and $25 a pound. So if I were, if I had 20 minutes to get you a price on a complex piece of equipment and I didn't want to wait a month to get a bid back, I would find out how much it weighs and put it in that range there.
Great, thank you. Those are all the questions we have. Again, want to thank everyone for joining us today, and a quick reminder that we do have another webinar coming up the 8th of December. That's designing complex distillation systems for difficult separation, purification, and the recovery of valuable chemicals. An invite will be coming out shortly for that. If you do want to reach out to Chris, his email address is below, chris.rentsch@kochmodular.com. Feel free to reach out to him. And thank you very much, and have a great Thanksgiving. Take care, everyone.
Bye.